Let's finish off this idea of the Bronsted-Lowry acid-base concept, and the last thing we want to talk about here is this idea of conjugate acids and bases. So, as we saw when we were identifying in our acetic acid reaction here, that hydrogen acetate, or acetic acid, was our acid in the reaction by definition because it donated an H+. In that forward reaction as well, water being the proton acceptor was defined as our base, and we see logical products because of this. There is another way to look at this one, and if you take a look in particular at acetic acid and acetate ion, you will see that they are related, as one is an acid in one half of the equilibrium reaction, and the other one is a base in the other part of your equilibrium equation. We call these conjugate pairs. In your acid-base reaction, there are always two acid-base conjugate pairs. When we take a look at these, we see that in this particular example, acetic acid is the acid, acetate ion is the conjugate base. All right? Whatever was the acid in one reaction becomes the base in the other reaction. So, look at water and hydronium. If water was the base in the forward reaction, then hydronium was the acid in the reverse reaction. Therefore, they make another conjugate acid-base pair. Each reaction will have two conjugate acid-base pairs. And we can use the relative strength of the acids, which we'll get to in a table in our data booklet shortly, to predict where equilibrium will lie. But the equilibrium position will always favor the weaker acid and the weaker base. So, where does equilibrium lie? Well, if we take a look at this one, you have two acids, acetic acid and hydronium. Which one do you think is the stronger of the two acids? Well, acetic acid, tasty vinegar, something that we can use to make pickles and delicious chips and things like that with, or straight up hydronium, which is our indicator of acid. I think we can get there, and we can predict that it's hydronium. So, if hydronium is the stronger of the two acids, it is the more aggressive proton donor, and we should see that the reverse reaction is the more favored. All right, between the bases, which do you think is a better proton acceptor? A neutral molecule of water or a negative ion? To your negative ion, this should be the better proton acceptor, so your stronger base is also here on the product side, and therefore we should see that it is the more aggressive in accepting hydrogens, and therefore we should see a push to the product side. So when we say that equilibrium favors the weaker acid or the weaker base, we're talking about the amount of material. If this reaction between hydronium and hydroxide is more aggressive, you will produce a lot more acetic acid and water. We see this here, and this is also reflected in a data table that we'll get to in a bit, that the forward reaction, because again, we looked at things from left to right, we only get 1.3% of our acetate producing hydronium. So that must mean that as we make this product, the products are much more reactive, and they immediately become our reactants again. Again, we have the two reactions. So, which is the easier to do, which has the lower activation energy? This one right here. And so we sit with a whole bunch of dissolved acetic acid and water, and we get very little acetate, ion, and hydronium, because when these guys meet, they more successfully react. So, when we say equilibrium favors the weaker acid and the weaker base, when we're looking at it from that point of view, we're talking about the amount, which is the same way we looked at equilibrium in chapter 15. All right? In this Bronsted-Lowry idea, when we're looking at proton transfer, the stronger is the more aggressive donor and acceptor. The weaker, of course, doesn't do it as well, and so you can see the reason why we get a particular position of equilibrium. All right, identifying the conjugate acid-base pairs then, if we take a look at these examples, here I have the generic formula for an acid, H and A for whatever acid you've got, hey, there's another way to write water as HOH. And so when you take a look at the other side, you can see water has gained, HA has lost, and so my proton transfer went this way. And so HA, being the acid on one side, leaves us with a conjugate base of A- on the product side. Here you can see one that doesn't involve water. We can still find the conjugate acid-base pairs. Here you have HA- and HB-. You have two negative ions that contain hydrogen, but if you look at it this way, HA has gained a hydrogen. So that means the proton transfer went this way, and HB was our acid, therefore B2- is our conjugate base. And we could say the same for the other two. If water was the base on this side, then our conjugate acid is the hydronium. If HA over here was the base on the forward reaction, then we've created a conjugate acid on the product side. Okay, so there are always two pairs in a Bronsted-Lowry acid-base reaction, and it really does make sense. When we're going to look at where equilibrium lies, we're going to compare the two, the base and the conjugate acids for both sides, and we're going to look for which is stronger and which is weaker. Quick review, quick reminder, again, this is still just Chemistry 20. Strong acids are things that react quantitatively. There were 6 of them. They are all on your data sheet and you remember them. What we're doing now with the Bronsted-Lowry concept primarily relates to weak acids. These are the things that we ignored in Chem 20 because they existed in equilibrium systems. Equilibrium systems, as you guys now know from ice tables and all the stuff we've been doing, is a little bit more complex, and so we've saved it here for Chemistry 30. Weak acids, because they react incompletely, form equilibrium systems. And equilibrium, with our ice tables and things like that, need to be treated a little differently for their stoichiometry. So what we're going to be doing now is really just looking at our weak acid systems and our weak base systems to be able to try and understand them a little bit further. We will use the acid-base concept from Bronsted-Lowry as proton transfer to help identify them and predict products. And from here, with equilibrium, we can take the stuff we learned in Chapter 15 with ice tables, stoichiometry, and some of our assumptions to be able to figure out relative quantities. Before we do that, please take a look at page 722 and 731. Try some of the practice problems and just make sure that you can identify acids, bases from the Bronsted-Lowry idea. Make sure that you can identify proton transfer, and just looking at it from kind of a different point of view, looking for acid conjugate base connections across an equilibrium system. Okay, there you go. That's the first part of 16.2. Lesson 2 will include a 5-step method, so identifying entities and things like that, very similar to what we did with electrochemistry, and we will start making predictions of what an acid-base reaction should and could be when we have multiple proton donors and acceptors available to us. So this should feel a lot like stuff we've done with electrochemistry and should be very doable for us. Okay? There you go. That's the finish for Lesson 1 of 16.2. The next videos will be the 5-step method. We'll call it Lesson 2 of 16.2. Good luck with it, guys. Try some of this and then move on to the next lessons.